Okay, as promised, we're going to look at a numerical example of the previous two-body problem. And so we'll include masses for these objects. There's the pulley. Instead of writing mass 2, we'll have, let's say, 5 kilograms. And maybe we'll have 6 kilograms here. Now, it doesn't matter how heavy it is because there's no friction. And we'll make a note of that. No friction here, so that doesn't matter how heavy the 5 kilograms could be 1 gram, and it would still pull it, just that it would pull it very slow. Now, if you wanted to solve this without going through the entire derivation and use the numbers directly, that's what we're going to be looking at. So we'll draw, again, step 1, draw the free body diagram. Step 2, write the second law equations for each mass. So here we have the 6 kilogram mass, and here we have the 5 kilogram mass. And just as we did before, we're going to have the same forces. We have a tension pulling on this one. Let me actually do that in red. There's our tension. It's sitting on a surface, so we have a normal force, normal meaning perpendicular, and it has a weight to it, which is going to be mg. And the second mass has the cable pulling up on it. That's a tension down. Those two tensions are the same. And it has a mass going down. Now, we actually know what the mass is here, so we don't have to write mass 1 and 2. We'll just use that directly. So now when we solve the equations, we can write the sum of the forces in the x direction equals ma, which is going to equal 6a, and the tension is just T. Now, we can't get any further than that. In the y direction, we know that it's not moving from our previous diagram. There is no vertical acceleration on this. It can't go up in the air. It can't fall through the table. So there is no acceleration. So we'll just write that. And in the y direction, we're going to have 0. We're going to have the normal force minus mg equals 0, or the normal force equals mg. Let's just extend that a little bit. And that will then, and we can actually calculate that directly now. So that's going to be 6 times 9.8, which is, let's see here, we have 6 times 9.8 is 58.8. So we have 58.8 newtons. In the second mass, we can write the sum of the forces equals ma. Again, we know this is now 5a, and we've got 2. But remember, the object is moving downward. So downward is positive. That means this is positive. And let me just go up there a little bit. And this will be negative. So I've got minus t plus mg equals 5a. Now, again, we know mg for this one. Let's put it in there. T plus 5 times 9.8 equals 5a minus t plus 49, 5 times 9.8, and hopefully I'm correct there. That's 5a. And now, once again, we'll take t equals 6a and place it in there. So that, in fact, what we get is a minus 6a plus 49 equals 5a, or 49 equals 11a. And so we can see that we've got a equals 49 divided by 11, or the acceleration equals, let's get the calculator here, do do this correctly. 49 divided by 11 is 4.45. So we have the acceleration equals 4.45 newtons per kilogram. Now remember, this is in newtons, and this is kilograms. So we get newtons per kilogram, which, as if you remember, is 4.45 equivalent to meters per second squared.